Last video, we described how there are certain subshells and also principal energy levels. So we had shown that there was n is equal to 1. We showed there was n is equal to 2. There was n is equal to 3 in the Bohr model. But then in the quantum mechanical model, we could see that there were a variety of different subshells within those principal energy levels, so that n is equal to 1 actually has just this 1s subshell. N is equal to 2 has the 2s and the 2p subshell. N is equal to 3 has the 3s, the 3p, and also over here the 3d subshell. Now, these subshells all have different energies. I've drawn up, as we go up here, increasing amounts of energy for these areas where electrons spend their time around the nucleus. Now, let's say that you had hydrogen. Okay, so it had 1 electron in it. You know this because its atomic number is 1, so it has 1 proton and not being an ion. It has just as many electrons, 1 electron. That 1 electron, that goes into the 1s subshell if the electron is in configuration is in the ground state, where electrons are in their lowest energy positions. Now, we can describe this 1 electron being in this most comfortable position, this lowest energy position, in the 1s subshell, using this electron configuration. Hydrogen, its electron configuration is 1s1. And this is showing where the electrons are around the nucleus. When we write 1s1, we are saying that there's 1 electron. Okay, so in the top right, in this superscript, that number is the number of electrons within a subshell. There's 1 electron, represented by this arrow here, in the 1s subshell. So here is our 1s subshell, where 1 stands for the principal energy level, 1, and S stands for the subshell within it. Okay. Now, let's say that we had helium. Now, helium has 2 protons and 2 electrons. If there were 2 electrons, they would both be in the 1s subshell. You see, according to the Pauli exclusion principle, there can be up to 2 electrons in an orbital, and they must be of opposite spins. So we can see that this box, this orbital, it can hold those 2 electrons, and they're of opposite spins. One goes up in this drawing, and one goes down. This affects things like magnetism later on. All right, so we can describe the placement of the electrons in helium using an electron configuration. I mean, we could go and draw this whole thing out every time we wanted to talk about the electrons and their places, but it's a lot faster just to write an electron configuration. We'll say that there are 2 electrons in the 1s subshell. So there's 2 electrons in the 1s subshell. Now, being that there are only a possibility of 2 electrons in an orbital, we had drawn both electrons in helium in that orbital. But now as we move on to lithium, that next electron is going to go into the next lowest energy orbital. You see, the Pauli exclusion principle says there can only be 2 electrons in an orbital, and so the next electron has to go into the next lowest energy orbital. Aufbau's principle says that electrons enter the lowest energy orbitals first. So instead of putting some electron, say, up here, we're going to put it right here in the lowest energy position. Okay, so what is the electron configuration of lithium? It has 3 electrons. So the first 2 go in the 1s subshell, 2 into the 1s subshell, and then the next electron goes into the 2s subshell. So the electron configuration is 1s2, 2s1. There's 1 electron in the 2s subshell. How about beryllium? Add another electron, a total of 4 electrons, we get the following configuration. That's 1s2, 2s2. Next, boron. It's got 5 electrons. 2, 4, add a 5th. It goes here. In actually any of these 3, 2px, 2py, or 2pz. These are 3 different orbitals within the 2p subshell. This is the 2p subshell. It's all 3 of these orbitals. Each of these boxes represents an orbital. Now, there's the 2px, 2py, and 2pz orbitals. These are regions in which the electron spends its time around the nucleus. Each of these colors represents one of those regions. We say 2px because there is a p orbital on the x-axis around the nucleus. We say 2py because there's a p orbital on the y-axis around the nucleus, and then we say 2pz. There's a p orbital on the z-axis around the nucleus. So each of these boxes, each of these orbitals represents a region in space around the nucleus. If I were to draw the 2s, I would draw it as a region kind of like that. So that would be the 2s. And then if I were to draw the 1s, it would be in a smaller region around the nucleus. And if I were to draw the 3p, well, actually, let's go ahead and draw the 3s. The 3s would be a larger region. And then the 3p would be bigger than the 2p's. Okay, so now it's looking like a mess. But that's kind of the situation with electrons around the nucleus. They are distributed widely around the nucleus, although in each orbital they're in relatively defined spaces. Okay, so we've discussed the orbitals and their shapes. Now, the configuration of boron, we see it has 5 electrons, 2 in the 1s, 2 in the 2s, 1 in the 2p. So we write that 1s2, 2s2, 2p1. Now, add another electron. Where does it go? According to Hund's rule, it will go into the next orbital. Yes, not into this orbital where there was already an electron. You see, Hund's rule, aka we'll call it the bus seat rule, says that electrons spread out among orbitals of the same energy before they pair up, just like strangers won't sit next to each other, or shouldn't sit next to each other, on a bus until other seats are full. That would be a little bit awkward. Yes, this next electron, instead of going here in the same bus seat as this electron, it goes into another empty bus seat. And so if we wanted to be more descriptive, we might say the electron configuration of carbon here is not 1s2, 2s2, 2p2, but sometimes, particularly in college level chemistry, we would write 1s2, 2s2, 2px1, 2py1. Next, nitrogen would have an extra electron. It would go here. Now, oxygen, add 1 more electron. It does fill in one of these orbitals so that there are 2 electrons in the orbital. Eventually, if all of the bus seats are half filled, then electrons will start doubling up on those orbitals. And then fluorine, and then neon. Now, this is a very special situation right here. Neon is very stable. Neon has the 1s and the 2s and the 2p subshells filled. But more generally, it has filled principal energy level 2, which has the 2s and the 2p subshells within it. This is a noble gas configuration when an entire principal energy level is filled. That is very, very, very stable. And that is the reason that many compounds, elements will react with each other to gain a noble gas configuration like this. Now, back when we had helium, when it had just one, the 1s, and therefore principal energy level 1 filled, that was also very stable. Now, let's say we're going, this is not on our upcoming test on Chapter 5, but let's say that we had an electron, let's say we had sodium, and it had an electron in the 3s as well as all of these. Sodium would have a tendency of actually losing that electron so that it would have the same electron configuration as neon and have just a filled outermost noble gas, outermost valence shell, or outermost principal energy level. Yeah, we're going to refer to valence shells. A valence shell is the outermost principal energy level. So for sodium, it had one electron in principal energy level 3. That was quite unstable. Losing that, it had then just these 8 electrons in this principal energy level 2, the outermost principal energy level. A valence shell is the outermost filled principal energy level. Okay? And really, that's why this is all so important. Electron configurations define stability and the tendency of atoms to react. It's really kind of the central basis of this semester. All right, thanks for watching, guys.